we ready? Okay. Okay, thanks everyone for coming. My name is Patrick Cozzi, and I have Sean Lilley with me, and we're 3D developers at a company called AGI. This is the company that started Cesium. And today we're going to talk about what I believe is the next big thing in 3D, perhaps even bigger than Cesium itself, 3D tiles. And I think this is really the start of a new era for streaming 3D geospatial data, and I hope our ideas here will spur your creativity to really take this to the next level. I'm going to go over the motivation, the vision, and some use cases. And I'm going to pass it off to Sean, who's going to dive deeper into the technical details. So Cesium is an open source JavaScript library for doing 3D globes. About 5 years ago, our customers at AGI needed a cross-platform lightweight visualization engine. So we made Cesium really for the aerospace and defense market, and we focused on things like visualizing satellites and satellite orbits. Since Cesium's open source, today we've seen it used for a variety of use cases, literally every satellite in space to every building in Manhattan. So we see here 1.1 million buildings from OpenStreetMap being streamed to Cesium. We have users who want to do millions and billions of point clouds. Of course, traditional high-resolution terrain and imagery, 3D models that can be instanced, like trees, as well as traditional vector data, but vector data specifically for 3D, like air corridors and points, lines, and polygons clamped to terrain. So when you look at these use cases, they're very similar in some ways, and they're very different in other ways. When you look at the similarities, they're massive data sets. So you can't just download the whole data set at once, nor could you fit the whole data set into memory. So you need tiling approaches so that you can download just a subset of the data based on the view. And you need hierarchical level of detail so that you can load in high-resolution tiles that are close to you and low-resolution tiles that are far away from you. You need efficient culling so that we don't ask for or render tiles that are out of view. And we need fast ways to get the data to the client. So we need context-aware compression, and we need fast ways to render it. So we need WebGL batching and instancing. And these data sets, they're generally non-uniform. So we don't want a one-size-fits-all subdivision. Our buildings are not uniformly distributed in a city, and the number of triangles in each building is not uniformly divided. So we want the ability to do context-aware subdivision based on the input data set. And for most of these data sets, maybe with the exception of terrain and imagery, we want the ability to interact with individual features, such as individual buildings or trees or points, lines, or polygons, and to style them, to change their color, to turn them on and off. And the thing when you bring this together is I think it's a little bit of a buzzword, data fusion, but the ability to bring in these heterogeneous data sets into one viewer I think is really valuable. So when we look at traditional 2D tiling, you look at maybe TMS, for example, and in lat long space, we do a uniform quad tree. And this is pretty good for imagery, because imagery is pretty well uniform. Terrain, it works okay-ish, but you do have flat areas of terrain that wouldn't be many triangles. And then high-frequency terrain, there'd be a lot of triangles. So uniform subdivision isn't necessarily perfect there. And 2D is fairly easy in that for any given view, all the tiles are the same level of detail. When we go to 3D, we have a few problems with this traditional approach. One is a number of our data sets, they're non-uniform, so we could do a more optimal subdivision. Two is a lot of our data sets are truly 3D. So if we have a point cloud that's like a church, for example, we do want to subdivide along that height in X, Y, and Z, not just in X and Y. And then third, imagine if we had 3D buildings or 3D models in general, and what if that model was in two tiles here? Right? Do you store that in both tiles, or do you render it twice and download it twice? Then the other detail to look at, when you're in 3D, you're going to have multiple levels of detail in the same view that we're showing here in the bottom left. And you need an error metric to decide what tiles I should show up front and what tiles I should show in the distance, such as the view meets a certain pixel error or screen space error. So given all this, I think it's really good timing to introduce a new open format, because given that we have all these use cases, we have widespread adoption of Cesium and WebGL, the underlying technology, And the field has changed dramatically with the amount of 3D data that's now available. In fact, I feel like years ago, the software was ahead of the data, and now the data is ahead of the software. And 3D Tiles is our answer to bringing that streaming back. So 3D Tiles is an open specification for streaming massive, heterogeneous 3D geospatial data sets. I know that's a mouthful, but I feel like every one of those words is very important. I think it has the flexibility that we need to do a lot of different 3D data sets, and the client implementation is general, so that we can do one client and then many server-side implementations. So 3D Tiles is really two things. I mean, at the end of the day, it's a spec. The spec is on GitHub, and the spec is written in Markdown, and the spec defines a JSON schema for defining the tile set. That's the spatial data structure that defines the organization of the tree, as well as individual tile formats for the tile payload. So that's downloading batched models, instance models, point clouds, that kind of thing. The 3D model formats use glTF, the GL transmission format. That's an open standard from the Khronos group. The Khronos group does WebGL, OpenGL, Collada, Vulkan, and I was heavily involved in the ratification for the spec for glTF. And by using glTF, we're taking advantage of the glTF loader that's already in Cesium, as well as the really emerging ecosystem of glTF open source tools. And these tiles, when we download them, they're ready to render. We don't have to do a lot of processing. We don't want to do a lot of processing in JavaScript. And then the third piece of the spec is a declarative styling language. So these are small JavaScript expressions that have access to per feature attributes and then can change features color or show properties. And then for software, we have an open source implementation in progress, but very far along in Cesium. So one of the big ideas in 3D Tiles is that instead of just having this quad tree subdivision, we just have a general spatial data structure that just relies on what's called spatial coherence. So a tile's children, those children just need to fit in the tile's bounding volume. You could have as many children as you want, and they could be subdivided however you want them to be subdivided. They just need spatial coherence. And that gives the client a general traversal algorithm, but the server can create that data set in whatever way is optimal for the input data. So for example, in the top right here, that's a traditional KD tree, and maybe those non-uniform subdivisions are based on the cost of rendering features. In the middle is an oct tree, maybe a good solution for point clouds. In the bottom right is a loose non-uniform quad tree, which we use for rendering some types of buildings. And here's an example for the declarative styling. So in the top left, we see the declarative styling that's used to map building heights to colors. And the tallest buildings are also translucent. And then we're also mapping the area property to the show value. So we're saying show all the buildings that the area is greater than 0, really just for illustration. In the top right, we see a building that's highlighted on mouse over. That's not part of the declarative styling spec, but I think it's a really important feature of the interactivity for 3D Tiles. Okay, so the 3D Tiles status. So we announced this effort at the SIGGRAPH conference in August 2015. I think it got pretty good traction. If you look at the forum on the Google Groups, it has 2,400 views right now, and probably half of them are mine, so I think it's pretty good. We expect the spec to stabilize and the Cesium implementation to stabilize this fall. The main things that we need to finish is the compression and per point attributes for point clouds, clean up the instance model tile format, and do a vector data format, tile format. And the Cesium implementation at this point, it's like almost 1,200 commits ahead of master. It's fully unit tested and has reference documentation. And there are a ton of people who are already using it, which is like, it's super exciting. And yeah, it's really awesome. And I'm going to show a few examples of that before Sean goes into more detail. So the first here, this is AGI and our data partner, CyberCity. And they have 3D buildings. In the top left here, we see Washington, D.C. It's about 135,000 buildings, generally pretty light, maybe a few hundred triangles per building. And then we tile it up into a loose quad tree, stream it to the client. The input is really a CSV file with longitude, latitude, height, and Collada models. And then we create a 3D tile set. And then they also do styling. You see in the bottom right, that's Canary Wharf. styled based on altitude. The other thing we've done with CyberCity is we've added terrain. So now with the processing, we also add terrain data. We put the buildings at altitude, and then we drop a little skirt down for the geometry of the building so the buildings don't float above the terrain. This is Cambridge. I know it looks kind of flat, but there's a bump in the bottom right. Okay, so if you come 5 o'clock today, Matt Amato is going to give a talk on bringing OpenStreetMap to the third dimension, and this is Manhattan. I think it's actually most of New York City, 1.1 million buildings, dynamically styleable, really cool stuff here. We take an OSM extract from MapZen, convert each building to Collada, and then we convert to 3D tiles. This is OpenTreeMap from Xavier. It's 57,000 trees in Philadelphia. We export the data, and then again we create 3D tile set in here. The trees are instanced, so that means you download one tile and it has the tree model, but it might have hundreds of positions where you take that same tree and you duplicate it. So it's very efficient both for the download and for the interaction with WebGL. Here's Virtual City Systems. Stay in this room for their talk right after our talk. They're doing amazing work with city rendering for 3D tiles. This is Berlin, 540,000 buildings, textured from city GML, tiled into a 3-level hierarchy and streamed into the browser, preserving the city GML attributes. So here's examples for clicking on a wall or a full building and then showing the original city GML attributes. And I think bringing that data all the way through from its original source and then through to the client is key. Okay, City Zenith, they're building their smart city application on Cesium, again, streaming 3D buildings that are textured, and then using the Cesium API to do annotations, measurement tools, and that sort of thing. Fraunhofer, they're doing wind park planning with 3D tiles. So in this screenshot here, they actually have 3 different tile sets, one for the trees, one for the buildings, and one for the windmills in the background there. Then finally, Vricom, they have absolutely incredible terrain and imagery data, and they're streaming with 3D tiles, a fused tile that has terrain, imagery, and buildings with absolutely phenomenal resolution. So now I'm going to turn it over to Sean. He's going to tell you more details about the spec itself.
Hello, is this loud enough? Okay, just setting up the recorder mic. That's good enough. Okay, so yeah, I'm going to talk more about like the details behind 3D tiles, basically like a deeper dive into what it actually means to have a 3D tile set. So 3D tiles is basically composed of 2 different parts. There's the tileset.json file, which actually defines the spatial layout for the tile set, so it contains the bounding volumes and just like the tree hierarchy. And then it also points to the external tiles. And the tiles themselves actually contain all the data, and they have different binary formats depending on the type of data. And then we can have optional compression methods on that. So for example, we have the Web3D quantized attributes, which is just a way to encode the same data with fewer bits based on rendering relative to the center. And on the right, I show an example of how your 3D tile set might be organized. You have your tileset.json file, and it points to any number of other tiles that are inside this folder structure. And you don't have to have it organized exactly like this, but this is like a general approach that you might take. And in addition to that, you can also have a tile set file that references other tile sets. So for example, if you're rendering like the whole globe, the first tiles.json might be the whole globe, and then the smaller tiles.jsons at the bottom would be like individual cities. So if you zoom close to, say, one city, you would only be rendering that tiles.json, and the other ones would not be loaded until you actually get there. So now I'll talk about the different tile formats that we support. We have batch 3D model format. We have an instance 3D model format. We have point clouds. We have composite, which is like a combination of different formats. And upcoming, we are working on a vector format. And the batch and instance use glTF internally to render the 3D model. So the first one is the batched format. This is for the cities, pretty much. And yeah, the most common use case is for cities and buildings and things like that, where you have a lot of different models which you want to combine together. So the features, the individual buildings, are batched into a single 3D model. So say you have like 100 buildings in a small area. All those buildings will be combined into a single tile. And the goal behind this is we want just a single draw call for that tile. And we embed the binary glTF, so underlying those 100 buildings is just a single glTF model that's part of the tile. And the way that we differentiate the different buildings within the tile is we have a batch ID vertex attribute, which lets us enable per feature styling, and it also lets us show or hide certain buildings. It basically lets us say that even though they're all the same model, these vertices are for this building, and they have these properties. And in addition to all that, we have a batch table that's also encoded in the tile, and it stores the additional per feature attributes. So I'll get into that next. So some of the common attributes that we might want to store are like the name of the buildings, the descriptions, the heights, areas, longitudes, latitudes, like it could go on. Or if you just want to keep it simple, just have an ID and then query a third-party service just to get all your information. And so these values, these min and maxes, are stored in the tileset.json file. It just makes it easier for styling and other purposes to see, like, okay, the minimum height is 10 meters, the maximum height is 100, and then you can color it accordingly. And the batch table properties are stored as JSON, and it's just embedded inside the binary file. Okay, so that was for the batch format for buildings, and now this is the instance format, good for things like trees, stop signs, basically any repeating elements where a single model can be represented like hundreds of different times. So what we do here is we embed the glTF model directly in the tile, or we can reference it externally. And the tile itself stores the positions of all the instances, and it also stores the per instance data in the batch table, kind of like how the buildings did. And like the buildings, we want it to be as fast as possible. Our goal is to have a single draw call per tile. And the way we do this is we utilize the instance arrays extension for WebGL. So even though a single tile has, I don't know, hundreds of trees in it, it's one draw call in terms of WebGL. And one more format is the point cloud format. So it kind of looks like a solid surface, but there's just millions of points there representing the church. And the point cloud format is simpler than others right now. It's essentially just an array of positions and colors. And what you do is you take that data directly and you fill the vertex buffer and just render as points. And on top of that, we use relative to center for higher performance, or for higher precision and performance. And we're still working on this a bit, but it needs some additional compression, and we need to actually give attributes per point, which we don't do right now, but we're working on that. And then the composite tiles is sort of it's a format that combines other formats. So if you have all your buildings and trees and you want to combine them together, then you would want to use a composite tile. Some of the trade-offs are it's good because you can reduce the number of tile requests. So instead of loading the building tile and the tree tile, you can now just load the building and tree tile together. But there are some disadvantages, such as it's harder to find the ideal subdivision method, because now you have these different data types, and there might not be it might be harder to find a good method for subdividing. And you also have a little bit of less flexibility in hiding certain layers, so it's harder to hide the tree layer versus the building layer. But if you don't need that stuff, then a composite tile might be what you're looking for. Okay, so that covers pretty much the tileset.json, the tiles, and I'm going to go more into detail about how you might want to subdivide your data. And yeah, this picture kind of shows just the generic tree structure and the different bounding volumes that it can support. So each tile can be represented by like a box or a latitude, longitude region or a sphere. And in terms of actually splitting up the data, it can be whatever you want, really. So 3 examples here are just, you can do a uniform grid without any sort of like hierarchy, just grid it up. The quad tree, yeah, we all know that. KD tree is just non-uniform quad tree, pretty much. And so here's an example of like the grid layout. It's just you have your single bounding volume for the parent, and then I guess 50 or so individual tiles. And it's a flat tree structure. And this is actually the same city. It's rendered from a different point of view, but it shows the same data but organized very differently. So here you have an adaptive quad tree, and it's hierarchical. So it's a lot better for doing things like culling, where you can, if you're in the top right corner, you won't need to render anything in the bottom left. And some more ideas for subdividing your data is you don't have to follow like direct splits in the quad tree. If your content only fills a portion of the region, you might want to, I guess, constrain it to a smaller region, just so it's better for culling, especially just not having to have a bounding volume that actually exceeds what you need. So here's one picture. Maybe a little hard to see, but in the bottom left corner, there's like a red bounding volume that's inside the main bounding volume, and it's smaller because the buildings in that tile don't extend too far outward. And so another approach you might take is a loose quad tree approach, where this is mainly useful for not splitting buildings that cross the tile edges. So in this picture, the arrow is pointing to a green building, which normally would have been cut straight in the middle. But the goal here is it's not really good to do that. Then you have to either render the building twice or split the building in half and have the model halves be rendered. And it's just a mess. So the flexibility of 3D tiles is that you can have the different child tiles overlap each other, and you can have the building only exist in the left tile. And then just the last thing is you can have an octree type structure. It doesn't have to be like 2D splits. In fact, sometimes you're much better off with like an octree to be able to split in 3D space. So yeah, the point cloud is like a good example of that, where it wouldn't make sense to split this in a grid or something like that. Like you really need the third dimension to properly, I guess, subdivide it well. So now I'm going to talk a bit about, at least in Cesium, what we do to speed up the rendering of 3D tiles. So culling is the most obvious optimization we can make. So yeah, when you're out from this angle, you render all the tiles, but as you zoom in closer, you only render a much smaller subset of the tiles. And then level of detail. So what happens when you zoom in and out? Obviously, you don't want to, like for culling, you don't want to render everything. And you might have higher level models or lower level of detail models, and you don't want to render the high level of detail when you're like super far out. So what we do is we refine based on a geometric error. So each tile stores its bounding volume as well as a geometric error. And this is used to compute a screen space error that basically tells us if this tile is going to be visible from that point of view. And if the screen space error is met, we refine to that tile. And we have two choices here. So the most common technique would be replacement refinement, where once you get close enough, you replace the tile with just the lower level, higher resolution tiles. This is like the traditional 2D approach. And then one issue here is you have to wait for all the child tiles to download first. And that's where additive might be a good alternative for this, where new tiles are rendered on top of existing tiles, and the child tiles can be rendered immediately. So I'll go through an example of that. So here is, you're pretty far out, and it's only rendering the root tile. And the root tile contains like the most important buildings, the ones that you expect to see from afar. And then after zooming in, you start to load the next set of tiles, so the child tiles start to load in. And it's adding on top of what was already there. So the root tile is still being rendered, and now you're rendering the child tiles. And then finally, zooming in closer, you just add on top the grandchild tiles. And actually, yeah, it's kind of, I think we have like 5 minutes, but basically we've been seeing a lot of cool stuff with 3D tiles. And I mean, I think the possibilities are pretty endless in terms of like representing 3D data. So if you enjoyed this session or if you have feedback, please evaluate it on the website and check out our arcade cabinet. And yeah, I'll just leave it here for questions. answer that?
So certainly simple quantization, I think will go a good way because we want something that decodes very quickly or even for free and can even stay compressed on the GPU, which is the compression that Sean talked about for 3D models. But we also want to talk to the people in the cloud community and see what can be implemented efficiently. It's already out there, but can be done efficiently in JavaScript. More questions? Another question. So for the vector format, we could use GeoJSON, but one of the main tenets behind 3D Tiles is we want it to be ready to render. So when it comes down to the browser, we don't want to have to process it. We don't want to burn the CPU. So we want it to be as close to GL as possible. So certainly someone could do that tile format. That could be like an extension, and that would be fine. I don't think you'll see the core 3D Tiles team doing that on the initial release, though. I think it'll be custom and made for 3D. And it will also include a geometric error to drive that LOD refinement, which is generally missing from all 2D vector data. Questions? Any more questions?